It's an error. Oops. Okay, thank you very much. Thank you for this introduction. It's very bizarre to have this headphones, but okay. So the idea is to give 4 introductory lectures on dynamical degrees, which is a core concept in algebraic dynamics. And it will be followed by 4 talks, 4 lectures by Serge Quentin next week on more advanced aspects on dynamical degrees. Okay, so this notion appeared first in 1997 in a paper by Russakovskii and Shiffman. And its main properties were exhibited in subsequent years, 2004, 2005, by Dean and Sibony, and then Dean and Nguyen, over the field of complex numbers. And then in 2011, 2012, it was extended to arbitrary field by Thuyen Truong and Nguyen McDong. And recently there was some very important and deep result by Junichi. Are probably going to be detailed by Serge next week. So this dynamical degrees, I'm going to talk about dynamical degrees attached to a rational map over a projective variety, but you have to understand that there are some generalization of this which I won't talk about. So you can talk about arithmetic degrees, relative degrees, and so on. So I won't talk about this. I will only talk about basic definitions, some examples, and of this dynamical degrees. Okay, so the context is algebraic dynamics. So what I mean by this is that I consider X up here an algebraic variety, but I'm going to simplify in this in my lectures. I'm always going to assume that X is a projective variety defined over C. I only know one field, C, characteristic 0, of dimension, let's say D. And for the moment, I'm going to assume that it's also smooth. Okay? So X is irreducible in particular. Okay, and I want to do dynamics, so I have to pick some self-map from X to X. So soon enough, it's going to be rational, but let me assume for the moment that this is just a morphism. So I want to look at the iterates of F to the n, is F composed with F n times. So there are many questions that you can ask when you're doing dynamical system. Basically, you want to understand the structure of the orbits. So here I would like to give you 2 motivations why we could be interested in looking at dynamical degrees. So the first thing is counting periodic cycles. So you fix any integer L, at least 1. And so you can look at the set of periodic points of period L. Period L cycles. So there are a set of points P inside X such that FL of P is equal to P. So this is algebraic. But in general, it has many components which could be of positive dimension. So not really in this case, but when f is rational. And so I'm going to look only at the isolated component of this, of dimension 0 component of this set. So the set of isolated periodic points of period L. So a 0-dimensional component of this set, let's say PL. And the basic question would be, how do you count this number? Maybe you don't have an exact formula, but what is the asymptotic of this, the cardinality of the point of period L as L tends to infinity? So estimate the growth of cardinality per LF as L tends to infinity. So this is a very basic question in dynamics in general, most, and here I'd like to ask it in this algebraic setting. Oops. Hello. There is another thing. So here I'm going to use words I'm not going to define. I think that Serge is going to define them in more details. So here I'm interested in what I mean by ergodic theory. So the rough question here is, can we estimate the global dynamical complexity of F, I mean acting on X. It's not very precise, but in fact there is important notion, very classical in dynamical system, which is called this the topological entropy. Which is a number that you can attach to any continuous dynamical system on a compact space, which is exactly our setting here, our setup. X, recall that X is smooth, it's projective, sorry. And the topological entropy is some number which is in between, can be 0. It can also be infinite, okay? And it gives you somehow how chaotic. So the larger the topological entropy is, the more chaotic you have to, the more chaotic the dynamics of F is on X. So you denote this by H top of F. Okay, so then the more precise question is, can you estimate, can you compute or estimate this number? So there are no good answer in this generality. Maybe for morphism, yes, but not for rational map, at least. But what I want to tell you is that in these two problems, there is appearance of some numbers. So that are denoted usually by lambda 1 of F, etc., lambda d of F, which are positive real numbers, at least one, called the dynamical degrees. And they turn out to be very important to control these things. Okay, so let me just give you one example. I think that Serge is going to actually prove this statement. That's the topological entropy. Okay, so here in the context I am here for morphism. It's actually the log of the max of the lambda k. And for rational map, it's only less or equal. And you have the similar statement for the number of periodic points, and I'll try to explain this a little bit in more detail later. Sorry, for k from 1 to d. D is dimension. So there is also lambda 0, but lambda 0 is 1. Okay, so I don't include it. Okay, all this is extremely vague. So I'd like to make some analogy between, let's say, algebraic dynamical system and, let's say, manifolds. So you have to think that the dynamical degrees, essentially, there are the Betti numbers. At least they play some kind of role of the Betti numbers of a manifold. Of course, so if you give the Betti number of some manifold, okay, this is important for what maybe if you want to distinguish two manifolds. So the classifications of manifolds. So if you have two manifolds with two different Betti numbers, that cannot be diffeomorphic. But also, if you have some specific structure, geometric structure on your manifold, then all the Betti numbers might have some special properties. So it reflects, in interesting circumstances, some geometric properties of the manifold. So here you can think of, well, I'll assume my manifold is a Kähler compact manifold. All Betti numbers are even. And here for dynamical degrees, it's about the same. So of course, just Betti numbers is a very, very weak invariant, okay? And dynamical degrees are exactly the same, but if it turns out that you have two dynamical systems for which the dynamical degrees are different, then it implies that f and g cannot be the same. They cannot be birationally conjugated. In other words, it can play a role in the classification up to birational conjugacy or even larger generality of rational map or endomorphism. And again, it's exactly as in the case of a manifold. Sometimes the dynamical degrees have very specific properties. So here, one example is like if you assume that f, so I think that Michel defined the Cremona group. So assume that f is a birational map of P2, so in the Cremona group of dimension 2. Then in fact, so here in this case, you have only one dynamical degree, lambda 1, because one can prove that lambda 2 is equal to 1. And here there is a funny thing, so I'm going to come back to this later, but for instance, lambda 1 is very special, is an algebraic integer. Even more, the Piso, Salem number, and so on. So we'll return to this later. Okay. Okay, so what is the plan of the lectures? It's a roadmap. So I'm going to talk about basics on rational maps. So I know that Michel did most of the work. Because looking only at morphism is too restrictive. If you're interested in the Cremona group, most of the dynamical system that you have cannot be made. You cannot conjugate them to a morphism on endomorphism on some birational model of P2 or even PD. Then I'm going to review somehow the first construction of Russakovskii Shiffman. I'd like to talk about dynamical degrees on the projective space. It's some kind of warm-up, and we're going to compute them in some examples. And then I'll turn to the case of birational surface maps. So essentially here I will discuss what you can say and the importance of dynamical degrees in the context where F is in the Cremona group in dimension 2. And then hopefully we'll define the dynamical degrees in general. So I will define dynamical degrees. For rational self-map on projective varieties. So basically only their definition. But so to get to that point, we need some information on intersection theory in higher dimension and so on, positivity properties. And so I prefer to postpone this to the last lectures. Okay, so but we already know what a rational map is, but let me say it very quickly. So, okay, so here we're going to consider, so let me start like 1 if you want, rational maps. I want to consider a rational map from a projective variety X to another projective variety Y. So if you have X and Y projective varieties, again over C. So projective means that you can embed them into some projective space of some dimension, right? So it's going to be important to sometimes to fix some ample line bundles. So recall that a line bundle is said to be ample if when you look at the the set of, for some power, the set of section does not have a base point. And if you look at the canonical map from X to the projectivization of the dual of the set of sections, this is an embedding. I'll probably have to put a dual here. Okay, so this is something which is P to some power H. So I'm not fixing an embedding, but projective meet X is some kind of subvariety in some P n pH for huge H. Okay, so as Michel said before, the rational map, you have essentially 2 approaches. So either you think of it as the data of an open Zariski dense subset inside X. Okay, again, here, at least I want X and Y to be normal and probably to be smooth. Okay, so open Zariski dense. And you have a regular map from U to Y. Modulo the equivalence is that if you have two representations like this, then you say that they find the same rational map if they agree on the intersection of these two open Zariski dense subsets. So the second approach is your map F now is determined by its graph, let's call it gamma, which is an algebraic subvariety inside the product x cross y, which should be reducible of the same dimension as x. So maybe here dimension is d. And so here you have two projection, right? You have the projection pi1 onto the first factor, x, and the projection pi2 to the second factor. And here what you impose is that pi1 is birational. Just as Michel explained, this means exactly the same here, but in fact, so you can find, let's say, u inside gamma and v inside x, such that the restriction, so open Zariski dense, such that the restriction from u to v is an isomorphism. Okay, so the way you go from here to there is you look at the set of points f of x, for x inside u, and then you take the closure. Okay, and from here to there, well, you play with this. You define f to be pi2 composed with pi1 minus 1 on the right on v. Okay, so just one thing. In general, gamma is not smooth, even if x and y are. Okay, so you have take the graph of. We're going to see some examples. For those you know, take the graph of a Hanon map in P2. It's not smooth. Okay. So I'm going to assume x smooth, and let me take f, a rational self-map from x to x. So I want to define an important locus, which is the locus of points of indeterminacy. And so I'm going to consider first the exceptional locus of pi1. So pi1 is birational. And so you can look at the set of point P inside gamma, such that pi1 is not locally an isomorphism. So this is an algebraic subset. And in fact, if you use the fact that x is smooth and you apply Zariski main theorem, you can detect when a point, at least when a point in the image of the exceptional set in pi1, so P in this side, the image of the exceptional set, if and only if the dimension of the fiber of P is positive. Okay. So the indeterminacy locus is precisely this set, the image. So it's a subset of X, and it's the image of the exceptional locus of pi1. So I'm going to denote it by ind of f. So it's pi1 of exceptional locus of pi. So this is smallest subset such that on the complement, F is in fact defines a regular map as above. Okay, so some facts. So one, the point P is in the indeterminacy locus if and only if it's imaged by F. So what is the image by F of a point when F is not well defined? Or you can look at this diagram here. So a natural way to define its image is that you pull back your point P by pi 1, and then you push it forward by pi 2. So you're in the indeterminacy locus if and only if this has a positive dimension. And this first fact is essentially a consequence of the previous remark. Second fact. So the exceptional locus is a hypersurface. Okay. It has codimension 1, but then you're mapping this by pi 1 to x, and here, so the locus of indeterminacy is of codimension at least 2. So again, the fact that x is smooth, at least normal, is important here. And the third general fact is that if you pick a point of indeterminacy, and you look at its image, f of p, so we know that it has positive dimension. And in fact, it's covered by rational curves. Oops. Okay. So there are only the last fact is so the second fact follows from the point that the preimage of a point is positive dimensional and that gamma is irreducible. And the last thing is here, it follows from, so this is true in any characteristic, but it follows from the fact that a birational map is dominated by a blob. So dominated. I'm not going to prove this. A rational map is dominated by a blow-up. And when you look at a blow-up, the exceptional locus is covered by rational curves. And so it's imaged by pi 2. The image of a rational curve is still a rational curve. Okay. So I will always assume that F is dominant. So here, by definition, this means that pi 2 is surjective. I didn't say very precisely. It could be dominated by a blow-up of a current sheaf of ideals. I think it's sufficient. But here it's also dominated by, if you want to use the general stuff, it's resolution of singularities and so on. It's dominated by a finite sequence of smooth blow-ups along smooth centers. I'll give you I don't want to discuss this. It's not central in my talks. And so I'm going to write down the set of references, and I can give you the reference for this. A book by Collar, for instance. Sorry? Yeah. No, birational, yeah, sure. Yeah. Sorry, yeah, birational. Otherwise, it's cannot be true. A blow-up is always birational. Okay, so dominant means F is surjective. So pi 2 is surjective. And when F is a rational map which is dominant, then you can start defining its iterate. So Fn is well defined. Rational map. So remember, so F was regular from X minus the indeterminacy locus of F, which has dimension 2, into X. So if you want to define F composed with F, you have to start with the point which is not in the indeterminacy locus of F, but also not in the preimage of the indeterminacy of S. Okay? And so here you better check that this is not the whole space, but we assume that F is dominant. So not every one can be mapped onto codimension 2 subspace. Okay? So this has at most codimension 1 and so on and so forth. You can iterate this construction. So Fn is defined on X minus union F minus K for K is equal to 0 to n minus 1 of the indeterminacy locus of F onto X. Okay. So we're going to define the dynamical degrees of a rational dominant self-map of some projective varieties. So before I do that, at least on P on the projective space, I'd like to comment a little bit on the existence of such objects. So I'm going to say that not all projective varieties admit interesting rational self-map. So let's look very briefly at the case where X is a curve. So if the genus is 0, X is a Riemann sphere, and any endomorphism of a Riemann sphere, let's say you have an affine coordinate that I call Z. Any endomorphism of Riemann sphere is in fact a rational function, P of Z over Q of Z, where P and Q are polynomials without common zeros. And this map is finite of some degree, so I'm assuming here that it's dominant. And the degree, let me call it D, is the maximum of the degree of P and the degree of Q. And when D is equal to 1, then it's a Möbius transformation. Otherwise, you have the dynamics is very interesting. And if I want to compare to the two to what I'm erasing here, then the dynamics is very interesting. The number of periodic points grows exponentially fast to infinity. It's controlled by D to the L. And the entropy is also positive. It's log D. Okay. So in the case where G is equal to 1, X is an elliptic curve. So it can be uniformized by C minus lambda, where lambda is a lattice, rank 2 lattice. And any map can be lifted to C as an affine transformation, AZ plus B, B in C, and A, some non-zero complex number that sends the lattice into itself. And then again, so here it's less interesting because the dynamics on the affine map is too well understood, but when you go down to the quotient, to the compact quotient C mod lambda, the dynamics is also very interesting. Positive entropy, exponential growth of dynamical degrees. And so here the topological, so there is a topological degree. Oh, this should be a torus. So what is a topological degree? You pick a point and you count the number of preimages. And here the exercise is that this topological degree, let me call it D, is the absolute value of A to the square. So when this is larger than 1, then the dynamics of F is interesting. Okay, and then there is a case where G is at least 2. And here you have to keep in mind that, in fact, there is no interesting rational map, no interesting endomorphism. So if F is a rational map, dominant, then in fact it is an automorphism of finite order. So F is an automorphism, and there exists some n such that F of n is the identity. Okay? So there is no dynamics on the curve of genus at least 2. So I have no control about the time. So I've been talking for 35 minutes, right? So I'm not going to do much on the classification of rational maps and so on and varieties, but I find it still a little bit interesting for people that have not looked at this to at least explain why for curve of positive genus you don't have any interesting dynamics. And the ideas, in fact, can be generalized to any dimension, right? So how do you show, well, or sketch a proof of this? So you pick a holomorphic one form on X. So you know that since the genus is at least 2, you have a lot of them. And non-zero. Yeah, I have to be careful because you have some Bourbaki spies in the room. So, so you can look at as the divisor of omega, which is a set of the divisor of poles and zeros of omega. And so this is an effective divisor. It's non-zero. And now what you can do is that you can consider the pullback of omega by F. So this is still a holomorphic one form. It has its own divisor of pole and zeros. And so you can compute, actually, what is this? Well, this is, so locally, omega is h of z dz in local charge. And the pullback of omega, this is h composed with f prime of z dz, right? And so you see that if you forget about this, then you get first the pullback of the divisor of zero and poles of omega. Well, here I'm saying poles, but I don't know why I'm saying poles, because this is a holomorphic one form. Yeah. So it's a pullback of the divisor of omega, and plus this extra stuff that comes from the points where the derivative is 0. So the critical set of f. So let me write this as a critical set of f. Okay? So now what you can do is to take, you compute the degrees. So if you have a divisor, sum of AI, PI, the degrees of some of the AIs on both sides. And so here, what's happening? So here, this is a degree of any one form to G minus 2. And here, what you get is you're pulling back some divisor of the degree to G minus 2. So here you get the topological degree of f times 2G minus 2. And here, this is something which is non-negative. So when you look at all of this, then this has to imply that the degree of f has to be equal to 1. Meaning what? Meaning that f is an automorphism, so that this is equal to 0, right? Okay, so we proved that Any self-map on a curve of genus at least 2 is an automorphism. Then you have to prove that the group of automorphisms is also finite. I won't talk too much about this, but so for instance, you can use the fact that X is hyperbolic, and the group of automorphism is a group of isometry for this hyperbolic things, and so it has to be compact, and using this, you show that it's finite. I'm not going to insist on this. The main point here is that this kind of statement, so it looks extremely elementary, but in fact, you can extend it to any dimension, and this is a theorem. Well, it's not even the strongest form of their theorem, but it's a theorem of Kobayashi and Ochiai. So I have to apologize in advance. I always make mistakes about spelling Ochiai. So if someone knows exactly how it's done, so theorem. So assume that X, so smooth projective blob of dimension D is of general type. Then any dominant rational self-map is in fact birational. So F from X to X, dominant rational map. Then in fact F is birational. So it's not necessarily regular, but it's birational of finite order. Okay? So what does it mean to be of general type? This is a generalization of curves of genus at least 2. So for those who know, so it's a Kodair dimension of X is equal to the dimension. Okay, great. Or if you look at the canonical bundle, which is the line bundles of holomorphic D form, then this is big. So, of holomorphic D forms is big, meaning what? Meaning that it dominates some ample line bundle. So for instance, if Kx is itself ample, then you're general type. Okay? Yep. Sorry? K, more effective, but the difference is effective. So if you want Kx is equal to A plus E, A ample, and E effective. I'll return to this, and so it's not really, again, it's not essential, don't worry. If you don't know what a variety of general type is, you're going to survive. We're not considering these maps, these varieties. Okay, so what I want to say, yeah, other facts. So for instance, if X, you can, a very important class of varieties is a generalization of elliptic curve to any dimension. So if X is an abelian variety, what is it? So it's a compact complex torus, which is also projective. So it's a quotient of CD by some lattice of rank 2D, which is also projective. So there are a lot of there are rational maps, endomorphism, exact, just like as before. You can so for some abelian varieties, the set of all endomorphism is pretty rich, especially those that arise from in the context of algebraic number theory. And sometimes it's pretty small, and you can only assume that this number a there is an integer. But what I want to say here is that if you take any rational map from an abelian variety to itself, then it has to be regular. It is a morphism. Why is it so? Well, if it had a point of indeterminacy P, you know that its image is covered by rational curve. So you should have a rational curve on an abelian variety, but it's not possible. Okay? So because X does not have any rational curve. Okay, so then, of course, everything I say here is pretty, well, it's more or less elementary. But what you feel is that there is a natural question is that can you, in fact, classify or characterize all projective variety that actually carry some interesting rational self-map? Okay, so, general problem. Let me put in question mark, right? So classify those projective varieties. Carrying interesting rational self-maps. So there is no, I mean, since the question is not well posed, there is no answer to this, but there are a lot of works in this direction. So I'm not going to be super precise, but let me just give a couple of references. So this question is pretty well understood in the case of surfaces. So the birational case was extensively treated by Serge Cantard. And it was also treated for endomorphisms. So the characterization of all surfaces, let's say normal surfaces that carry a dominant, not rational, but endomorphism, so morphism, was there is almost a full classification by Nakayama. I think there are a lot of Nakayamas. Here is Noburu Nakayama. In higher dimension, the situation is not well understood. There are a lot of partial results. I'd just like to mention some names here. So there is very important works by Diki Zhang, Ogizo, again Nakayama, again Serge Cantard. And since we have the pleasure to have Serge Cantard here, you better ask him for more references. Okay. So what you have to think about all this is that, so dynamical degrees for a regular map is, as we're going to see later, it's a bit too easy. So it's really essential when you look at rational maps. And what I said more or less is that the space where you have the more chances to have interesting rational map is projective space. So we can always assume that X is a projective space. It's quite safe. Okay? So this is the most important example. But so now you're wondering why there is a third part. I mean, the second part is dynamical degrees on rational map. It should stop here, okay? So the point is that if you want to understand dynamical degrees, you have to extend the map, not look at only maps from the projective space to itself, but also on varieties that are birationally conjugated, birationally equivalent to PD. So it's essential to look at map induced on every birational models of the projective space. So what I'm saying here is that it won't be sufficient to look only at rational map on PD, but you will have to extend them to extend the theory at least to all rational varieties. Okay. Okay, so you're going to see soon the definition of the dynamical degree. And again, before I do that, I'd like to stop and ask the following question. Why do we bother looking at rational maps? Okay, so there is this, you can look at the set of, let's say you have X, your favorite projective variety. You can look at the set of all endomorphisms. A regular algebraic map from X to itself, okay? So this is a subset of the set of all rational, so here I'm thinking dominant all the time, so rational self-maps. But it's also a subset of the set of all correspondences. I didn't define this properly, but so what is correspondence? It's again a graph determined by a graph, let's say gamma, dimension D, on X cross X. But you don't assume that the first projection is birational. You only want the first projection to be, let's say, generically finite. If you're Fulton's book Lover, then you even have a much more general definition of this set of correspondences, but let me just take this one. So here, pi 1 from gamma to X is generically finite. Okay. So in the invertible case, we are looking at automorphisms. Here, birational map. And here, if you want, is finitely generated subgroups. Of the group of birational transformations. So, question, so why are we interested in birational maps and not develop only the case of automorphism? Well, so the answer is here could be the following. If you look, for instance, at this famous example, projective space dimension D, here you have a very well-defined group, which is very small, GLD plus 1. On the contrary, the group of birational maps is much, much bigger, much richer. This structure is much more interesting. So looking only at automorphism is probably too restrictive. Okay, so you have to understand also that it might happen that another thing is that the dynamics of automorphism in PD is trivial. It's linear, so it's not very interesting. Entropy is 0, you don't have growths of periodic orbits. It's not exactly the case. You might have even over P2, you might blow up P2 at 10 points, very well chosen, and find some automorphism that have positive entropy. Dynamics is very interesting. But still, it's very hard. It's very few examples of this. So here, on the contrary, birational map, you have a wealth of examples. Okay, so now you say, okay, but why not looking at developing the whole theory directly for finitely generated subgroups and so on? Well, let's say the idea is that if you want to understand the structure of these groups, you better understand the dynamics of just one element. Okay? So if you want to go there, you better understand this first. Okay, here it's going to be a little the same. So for dynamical degrees, we're going to see that dynamical degrees for endomorphism are well understood. Here we have the definition of dynamical degrees, but then the theory is not well developed. And for correspondences, this is even more open. So there are very, very few results for correspondences. So I'm going to focus to only a rational safe map, and not necessarily birational. Yeah, I wanted to write down a couple of names to say that dynamical degrees were also defined and studied for correspondences. So you have some work by Dean and Guyenne. And there are a series of work by Sarah Cook and Rohini Ramadas on the computation of the dynamical degrees of some interesting correspondences. Yeah, and Thuyen also. Okay, so now I spent so much time saying blah blah. Then let me go now to the core of the lectures. That is the definition of the dynamical degrees. Or in the case of the projective space. Where is it? You here? So what was it? So 1, 2, I guess. So a dynamical degree or a rational safe map on the projective space of dimension D. Okay, so let me remind you what Michel's explained to us this morning. So F, rational dominant self-map from PD to itself. Then it's defined in homogeneous coordinates. So let's say Z0, Z1, ZD by D plus 1 homogeneous polynomials. So PIs are homogeneous polynomials of the same degree. Let's say degree of F. And I can always assume that they do not share any common factors. So without any common factor. So geometrically, what this means is that if you look at the locus where inside PD, where all these D plus 1 polynomials vanish at the same time, then this has codimension at least 2. This is exactly equivalent to say that they don't have any common factors. And what is this set? Well, this is exactly the indeterminacy locus of my map F. How do you check that F is dominant? Well, this is the same as saying that the when you look at the differential at a point, at least a general point, is non-zero. And so here it's equivalent to say that if you look at the determinant of the matrix of partial derivative of the PI with respect to ZJs, then this is not identically 0. So determining if f is, if I give you some explicit formulas, determining if it's birational, as Michel said, is very complicated, but determining if it's dominant is very easy. Another algebraic condition. Okay. Okay, so I'm going to define the dynamical degrees, but let me recall the question I was asking before, is counting the number of periodic orbits. So isolated period L. Okay. Okay, so the first thing is that, so we're going to relate this problem to the degree of f. And the first lemma, the first observation, is that if you compose two maps, f and g, two rational maps, again dominant, and if you look at the degree of the composition f composed with g, then this is less or equal to the product of the degree of f and the degree of g. Okay, so if you apply this to, I should not have taken this, but okay, let me write, sorry, h here. So take h to be the nth iterate of f, and g the mth iterate of f. And what you get is that the degree of fn plus m is less or equal to the product of degree of fn times the degree of fm. So in other words, if you look at the sequence of degrees of the iterates of f, this is sum-multiplicative. So un is sum-multiplicative. So there is a famous lemma or observation or exercise that when you have a sum-multiplicative sequence of, so these numbers, I didn't say it, but the degree is an integer, positive integer, right? So all these numbers here are positive integers. So when you have a sequence of positive numbers that are sum-multiplicative, then you can show that the degree of fn to the power 1 over n admits a limit. And we are going to define lambda 1 of f as being this limit. So usually it's referred to in the literature by Fekette's lemma. I never checked why it's referred to Fekete, but well. So this is the dynamical degree. And I put index 1 because as we shall see later, there is in fact 1 degree for each dimension, and this one corresponds to codimension 1. So this is a 1. Okay, so before I'm going on and look a little bit more at this dynamical degree, let me prove this this lemma and explain why, in general, this inequality can be strict. Yep. You need this. Okay, fine. Yeah, that's true. He's knowledgeable. Okay, so I'm not going to use this, but it's important in some application. Yeah, you're right. Okay, so how do you prove this this lemma? So it's completely in this setting is completely elementary. So you write H in homogeneous coordinates. So let's say H0 HD, G also G0 GD. So the HI are homogeneous polynomials of degree maybe D, maybe not D. Degree of HI. Okay, so this is degree of H. And the degree of Gj, this is the degree of G. And now you want to compose this H with G. So let's look at its description in terms of homogeneous coordinates. So you have to replace Z0 by G0, Z1 by G1, ZD by GD. So you get H0 of G0, GD, etc. HD of G0, GD. So what you see is D plus 1 homogeneous polynomials. So these are homogeneous polynomials. Of degree. Well, it's a composition of two homogeneous polynomials. This one of degree of H, this one's degree of G. So the degree is the product of the degrees. Fine. Okay, what can go wrong? What can go wrong is that a priori these new polynomials here might have some common factors. Okay, when you define the degree, you absolutely want this to have no common factors. So if these polynomials, let me give it a name. So let me, I didn't use it, I think, so QD, and this is Q0. So if the intersection of Qi equal to 0 from 0 to D has codimension at least 2, then fine. Then the degree of the composition is in fact the product of the degrees. Now what can happen is that they have a common factor. So otherwise, there exists, so if, now I have to remember all the letters of the alphabet, it's very difficult. P, Q, R, let's say R. So otherwise, there is some homogeneous polynomial. Of positive degree. So let's say a degree as least 1. That's that R divides H composed with G, well, sorry, Q naught, well, Qi for all I. In that case, the degree is strictly smaller. So what is nice is that you have a geometric, an easy geometric interpretation of this when this happens. So look, so this is PD. Let's look at the locus at the hypersurface defined by R equal to 0. So it's mapped somewhere. I should put dots by G and map somewhere by H. So what's happening is that when you're a point on R equal to 0, where outside the indeterminacy locus, so this is codimension 1, the indeterminacy locus has codimension 2, so you have many points like this. then after applying G here, so you get a point for which H0 of this, H0 is always equal to 0. What? So it means that the image of this hypersurface is something, and this something has to be inside the indeterminacy locus of H, which is a set where all these polynomials vanishes. Okay, so we learn a little bit more with this argument, is that in fact we have inequality, but also we have equality most of the time, except if some very specific dynamical thing happens here. So so the lemma, so the degree of G, H composed with G is strictly less than the product of the degrees if and only if there exists some hypersurface V such that its image by G sits inside the indeterminacy locus of F. Okay, so here I have to be a little bit careful with the notations. Is that here it's not what? H. Yeah, this is. So here I have to be careful. Here I put a check here, because I define the image of a point as being the total image, and here I have to take the strict transform. So what is, just to make things clear, so what is G check of V, or let's say of a point, well, of V. So suppose V is not included inside the indeterminacy locus of G. Here I have pi 1, pi 2, and this is a graph. So remember that pi 1 is birational. So in the current, in my lemma, x and both x are p to the d here, but I'm just defining this notation in full generality for, let's say, any rational map. And so what's going to be G check of V? Well, so we know that pi 1 is, you're going to take the strict transform of V inside gamma and push it forward by pi 2, okay? So it's the image under pi 2 of the strict transform of V by pi 1. So what is it? So it's pi minus 1 of V minus the indeterminacy locus of G. Okay, and then you take the closure. Okay? Okay. Okay, so we have defined the dynamical degrees for a rational safe map of the projective space, and then I'm going to so we also have understood why the dynamical okay, so maybe I should make a couple of comments. Hello. Yeah. So let me continue. So what I said is that the dynamical degrees were important if you want to classify a dynamical system. So it's a very vague idea. So here the fact is as follows. So suppose that F is any rational map from the project which is dominant. And let me take G, a birational map from on PD. So G is birational. Then you can look at the dynamical degrees of F, but you can also conjugate F with G. It's still it's another rational map. And the claim is that the dynamical degrees of f is in fact the dynamical degree of the composition of g minus 1 f composed with g. So how do you see this? Well, it's a direct consequence of the lemma. So why is it so? Well, dynamical degrees are defined by looking at the degrees of the iterate, right? So we're going to compare the degree of Fn with the degree of the iterates, the nth iterate of this map. And then since you conjugate it by g, this is g minus 1 composed with Fn composed with g. Okay, so let's look at the degree of this guy. And we're going to be very clever and apply the lemma twice. So you can apply the lemma to g minus 1 composed with this map. So this is less or equal to degree of g minus 1 times the degree of Fn times g. And then you apply it in second time to this composition. So it's less or equal to the product of the degree of g minus 1, degree of g, and the degree of Fn. So we actually have a much stronger result that the dynamical degrees are abound on the dynamical degrees. But we have a direct comparison between the degrees of the nth iterate of the conjugate and the degrees of Fn. So if you take the nth root of this, let n tends to infinity, take the infimum. You get lambda 1 of g minus 1 composed with f composed with g, less or equal to lambda 1 of f. Okay? So take 1 over n and let n tend to infinity. Now you can apply this symmetrically. So by symmetry, lambda 1 of f is also less or equal to lambda 1 of g minus 1. Okay? So if you want, you write f as g composed with g minus 1 fg g minus 1. Okay? And so you get the equality between the two dynamical degrees. Okay, so now what I would like to do is start computing examples. So I'm going to spend a little bit of time. So I have, like 15 minutes left, or maybe less, 10 minutes. So the idea is to look, so examples. So I'm going to look at automorphisms of the affine plane. Then I'm going to discuss the case of endomorphisms. And then of monomial maps. Yoo-hoo. Okay, and in each case, we're going to compute the lambda 1 and relate to the growth of periodic points. Okay, so in 10 minutes, it's not completely clear what I can do. Let me think just for a moment. Okay. Well, okay. Okay. Well, fine. Okay. So let's look at the let me start with this. Okay, so let me look at the group of polynomial automorphisms of the affine plane. So here you're looking at maps f, x, y, which are polynomials. So pxy, qxy, and such that there exists that admits an inverse, which is also a polynomial. So there exists a g, let's say p hat, q hat, such that g composed with f is the identity, f composed with g is the identity. Okay, so there is a famous theorem by Young probably many proof of the theorem, but okay. Was proved during the World War II for some reason. And then that was, let's say, translated to, translated or more dynamical terms by Friedland and Milnor in the 80s. And that gives the structure of this group. And that says basically, well, if you take a polynomial automorphism of A2, then up to conjugate by an element in the same group, we get one of the following three options. The statement is like this. So suppose that F is now automorphism of the affine plane defined over C. Then up to then there exists G in the same group, such that if you conjugate F by G, then you're in one of the following situation. First situation, F is affine. So something ax plus by plus c, a prime x plus b prime y plus c prime, where a, b prime minus a prime b is non-zero. All coefficients are complex. So second thing is what? I said de Jonquière, but now I don't remember if this is the right term, but Q product, what is the right terminology? What? Triangular. Yeah, so let's be consistent. I think it's important. Triangular maps. So AX plus, so in this case, so here I didn't say, but the coordinates are X and Y. So here what's happening is that your the map is fixing, let's say, the X coordinates. X is mapped to AX plus Y, plus B, sorry. And then in the second variable, so Y is mapped to, let's say, CY plus P of X. So A, C, non-zero. And if you don't want to be in the first case, then probably you want a degree of P to be at least 2. Okay, and then there is a last case. And the last case, let me call it a generalized Raynaud map. So this is the most interesting, or, well, okay, or I should not say this, but okay. More complicated one. So then this is a composition of maps. H1 composed with H2 composed with HK. H for Raynaud. And what is, so this is a generalized Raynaud map is a composition like this, which is a pure Raynaud map. This is a map of the form h of x, y's map to, okay, so you switch the two coordinates. So there are many presentations, okay, but so let's say y is mapped, so x is mapped to ay. And then in the second coordinates, you're adding something like bx plus p of y. Well, okay, it's not completely optimal, but so let's suppose that a and b are non-zero. And here a degree of p is at least 2. Okay, so now I have 5 minutes to compute the dynamical degrees in all these cases. I can do that. Okay, so in the first two cases, it's pretty elementary. So yeah, so we want to compute lambda 1 of f, and we know that this is lambda 1. There is a big resonance. Woo, come on. Okay. I don't want to destroy the blackboard. Okay, so lambda 1 of g minus 1 composed with h composed with g. So what is the degree of this affine map? Well, easy, right? It's 1. And if you compose the affine map with itself, the degrees, so here in this case, the degree, let me call this phi, of phi to the n is equal to 1 for all n. Okay, second case. So what is the degree of this map? So if you want to compute the degree, you have to homogenize this and to look at the common degree of the three homogeneous polynomials that define this map in P2. And you observe that the degree of this map is actually the degree of this polynomial. When you iterate, what's happening? So this stays a affine map in one variable. And here you start with, let's compute the second iterate to see what's happening. So you have cy plus p of x. Okay, so this is the first iterate. And the second one is c times cy plus p of x plus p of ax plus p. Okay? So there might be some cancellation, etc., and so on, but at least the degree is less or equal to the degree of p. So here, the degree of phi n is less or equal to the degree of p for all n. So in both these cases, lambda 1 is equal to 1. Easy computation. So the only non-trivial computation is in the case of Hanon map. So I'm not going to explain how to do that in this general situation. This is going to be an exercise. But let's do the case where k is equal to 1. So phi is actually h of x. And let's even simplify. So assume a and b are 1. So yx plus y to the square plus c. Okay? So here I'm assuming that the degree of p is 2, a and b are 1. But it does not change anything. Okay, so then you compute phi to the second iterate of phi. So what you see is that each time you have to switch these two things. So y is the new thing. So x plus y squared plus c. I know it's probably not super easy to follow computation like at 3:30 in a hot room here like this, but I'm finished. And so here, what's happening? What you have to observe is that in the second coordinate, let me. So okay, so when you go to xy to this, y goes there, and here the point is that y goes to y to the square plus affine terms. Okay, so when you iterate, what you do is that you have to take this to the square, so this is x plus y squared plus c to the square, plus x plus c. X is y plus c. Fine. So when you expand this, what you see, you get y to the fourth plus lower order terms. Okay, so you can iterate these computations. And what you end up with is the following form. So phi to the n of xy. This is xn comma yn. And in fact, xn is a polynomial of degree 2 to the n minus 1. And yn is a polynomial of degree 2 to the n, but more precisely, it's a sum of y2 to the n plus lower order terms. Okay, so you write this, you prove this by induction. And so what this proves is that the degree of phi n is equal to 2 to the n for all n. And so lambda 1 is equal to 2. Okay. Great. Not 1. Super happy. So that's why the dynamics is interesting. And just to, yeah, I should stop. But just to say what's the final answer here, what is lambda 1 when you have a generalized Helm map? Well, this is going to be the product of the degrees of this polynomials here. So let's say it's a product in general. This is a product of degree of hi for I1 to k. Okay? And yeah, let me finish here. Thank you. People are afraid. It was too easy for you, I know.
Okay, so you just did a little bit of yeah, you just did the computation for the dynamical degree of this MO map. But also you proved the lemma. You proved the lemma that the degree of H composed with G is the product of degree of H to degree of G if something happens.
Yeah, it was here. So it's going to be in the notes.
Okay. So the exercise is to extend the Helm map as a birational map of P2, write the formulas, and verify that the lemma applies, and you are in the case of equality.
Yeah. And also check that the graph is not smooth. Funny. Yeah. It's interesting to extend this to P2 and to try to understand in details how it's very explicit here. Not for complete composition, maybe, but at least even in the quadratic case, I think it's interesting. No? Yeah? What? Ah.
So you said the graph was not smooth. Is it like a multiplicity space?
It's not smooth in P2 cross P2 exactly at the point. So he knows that you have one point of determinacy for H and one for the inverse. And precisely at the point where in the graph that we have this pair of 2 point indeterminacies for H and H inverse is not smooth.
So it has a rational map of P2, so what's the surface?
That's a rational surface. What do you want to know? What is the singularity?
Yes.
You know how to desingularize a map, and so you should know exactly what is the. So the question is. It's in singular, it has a map to P2. What is the singularity, okay? And so the singularity is going to be a rational singularity and determined by its the dual graph of its resolution. I didn't know the exercise, but yeah, probably I can do it also. No. Be careful.
So you mentioned the monomial maps as well. So are you going to like do the similar computation or just leave that as an exercise?
Sorry, the generalized Helm map you said?
No. For the monomial maps, what happens with them?
Yeah, well, I can continue for an hour, but probably we need to have a break. So I'm speaking tomorrow, right? So tomorrow I'm going to discuss the case of endomorphism, which is completely obvious, but still, it's still interesting to balance out some things. And then of monomial maps, yeah.
Cool. Nice. Thanks.